Hi, everyone. I'm really happy to introduce today Sho Shibata, who is the new postdoc in my group. It just started in April 1st. Sho Shibata just got his PhD in March 2021 at the University of Tokyo under the supervision of Masahiro Ikoma. He also did in Tokyo, the University of Tokyo, his undergrad and master. He's working on planet formation, structure, and exoplanets. He visited Zurich a few times before, and we are all very happy to have him here. And today he's going to tell us about the evolution in chemical composition of gas giant planets, the effects of planetesimal accretion. Thanks, Sho.
Thank you very much. Hello, everyone. I'm Sho Shibata, and as Ravi said, I just started to work in this university from this April as a postdoc of Ravi, and nice to meet you guys. And 2 years ago, I visited here and stayed for 3 months. At the time, there are no pandemic, so I enjoyed the life in Zurich. It was a very, very good time. So I'm glad to come back here. I'm very happy. And so I will talk about my recent studies today, and it includes work I did in the my stay. And thank you for giving me a chance to talk today. And as I said, the title is Evolution in Chemical Composition of Gas Giant Planets. When I was a PhD student, I worked on the composition evolution of gas giant planets. So this is this talk gathers the work I did in my PhD course. Okay. And before start my talk, let me introduce myself first. Again, I'm Sho Shibata from Japan, and my name is written in many characters in Japanese, kanji, hiragana, and katakana. But of course, please use English alphabets for my name. And I took my PhD in last month in the University of Tokyo. I born in Tochigi Prefecture. It's a very countryside area of East Japan, and I moved to Tokyo and lived there for 9 years. So I think Zurich have both sides of the city and countryside. It has a very beautiful nature and a very civilized areas. So yeah, I love Zurich. I can enjoy both aspects. And I think in Japan, this is a season of cherry blossom. And last weekend, I walked around and found some cherry blossoms in Zurich. So I'm happy. And if you know some good place for cherry blossom, please tell me. I will go. Okay, let's start my talk. As I said, I worked on the computational evolution of gas giant planet, but my main interest is on the planet formation theories. After the discovery of first exoplanet, 51 Pegasus b, the number of observed exoplanets is rapidly increasing. In the right figure, the confirmed exoplanets are plotted on the plane of semi-major axis and planet mass. There are many types of planets, such as super Earths or Neptune mass planets and gas giant planets, and close to or far from the central star. Each planet is considered to be formed through various physical mechanisms. The final goal of planetary formation theory is explaining the diversity of exoplanetary systems. Today, I want to focus on the formation of crossing gas giant planets. These planets are observed with a radial velocity method and transition method. So we can use many observational values for these planets, such as semi-major axis and planet mass and planetary radius. We want to know where and when those planets start their formation in protoplanetary disk and how evolve with time. And many studies try to obtain the information of the formation stages of those planets using the observed physical values. But for these observed planets, more than 1 billion years have passed since their formation stages. And initial conditions of planet formation are not shown in this figure. So we need to go back in time and retrieve the information in the formation stages of these planets. But it is not so easy process. Sorry, wait. Okay, in the standard model, a standard formation model, planet formation starts from the dust coagulation and planetesimal formations. Once a protoplanet forms, protoplanet's mass increases by solid accretion. And if the protoplanet reaches so-called critical mass, it starts rapid gas accretion. This gas accretion is slowed down by the opening of this gap and stops by the disk dissipation. There are many physical processes in planet formation, and we have to solve many problems related to each processes. But today, we focus on the late formation stages of gas giant planet. In classical model, orbital distance of forming planets from the central star does not change during the formation stages. For example, Jupiter starts formation at 5 AU and finishes its formation at 5 AU. This classical model can explain the qualitative structure of our solar system, but cannot explain the formation of close-in gas giant planets found in exoplanetary systems. So after the discovery of close-in gas giant planet formation theory needs to consider the effect of planetary migration. Massive protoplanets interact with the surrounding disk gases gravitationally and change angular momentum, which results in the change of semi-major axis of protoplanets. Planetary migration makes the formation of close-in gas giant planets possible, but it also makes the evolution pathways of gas giant planets complicated. After the formation of massive core, the protoplanet starts runaway gas accretion and increase its mass. At the same time, the protoplanet interacts surrounding this gas and migrates inward. The formation process is finished by the disk dissipation. As a result, the protoplanet takes evolution pathways like this figure. Unfortunately, the current theoretical models contain many uncertainties, and gas accretion rate and planetary migration rate depends on the disk structure and parameters, such as disk viscosity. So only the observed planetary mass and semi-major axes are not enough to retrieve the information of planet formation. We can not constrain which evolution path is correct or not. It's a very difficult problem. To constrain which formation pathways did an observed planet take in the formation stage, we need to use the other information of exoplanets, such as planetary composition. Protoplanets accrete surrounding materials during the formation stages. The composition of disk gas and disk solid materials changes with the distance from the central star. For example, there are ice lines of water ice lines. Inside the water ice lines, water is in the gas state, but outer the water snow line, water solid state. So the composition of solid and gas changes with the radial distance from the central star. And the accretion rate of gas and the accretion rate of solid also changes with time. So as a result of these accretions, the final composition of gas giant planets would reflect the formation pathways. For example, many studies try to constrain the formation pathways using the compositional informations. For example, Madhu et al. 2014 and 2017 investigated the amount of carbon and oxygen of crossing gas giant planets, changing the formation pathways of gas giant planets. And Notsu et al. 2020 also investigated the effect of formation location of gas giant planets on the final CO ratio. According to the results, the CO ratio or amount of C or amount of O can be useful to constrain the formation pathways of gas giant planets. So we expect that using the composition information of gas giant planets, we can constrain the formation pathways of crossing gas giant planets. And in this study, we focus on the bulk metallicity or total mass of heavy elements of crossing gas giant planets. After the end of the formation of gas giant planets, the radius of those planets shrinks with time, as shown in the left figure. This figure shows the evolution of planetary radius with time. Each line shows the cases of different composition of planets. If a planet contains more heavy elements, the radius of planet becomes smaller. So if we observe the planet mass and radius and age of gas giant planets, we can constrain the composition of gas giants of that planet. And Songen et al. 2016 investigated the thermal evolution of 47 crossing gas giant planets and obtained the amount of heavy elements contained in those planets, as shown in this right figure. As shown in this figure, crossing gas giant planets contains much heavy elements, and the amount of heavy elements increases with planetary mass. And the solid line shows the metallicity of planets. For many planets, the metallicity are higher than 10%. Such a massive heavy element or such a high metallicity is considered to be brought by solid accretion, not by gas accretion, because this gas contains only a few % of heavy elements. So only the gas accretion, such a high metallicity cannot be approved. So we need to consider the solid accretion, which can increase the metallicity of planets. We want to know, but it is not easy to accrete massive heavy elements as 10th Earth masses. And some of these planets contains more than 100 Earth masses of heavy elements, as shown in here. So we want to know how these massive heavy elements are brought into these crossing gas giant planets. And we expect that revealing the origin of massive heavy elements in these crossing gas giant planets, we can constrain the formation pathways of these planets. In the planet formation stages, there are two kinds of solid accretion regimes, Pebble accretion and Planetesimal accretion. Pebble is a small solid particles of millimeter or centimeter size. Pebble is strongly affected by a gas drag of protoplanetary disk gas and drifts in the radial direction in the protoplanetary disk very rapidly. As a result, much amount of heavy elements are supplied into the forming protoplanet, which results in the very rapid accretion of solids. However, as the protoplanet grows, a gap structure is formed in the protoplanetary disk. This gap stops the radial drift of pebbles, and the protoplanet cannot accrete pebbles anymore. So solid accretion stops at this stage. This phenomena is called Pebble isolation, and the isolation mass of planets is a few tens Earth masses, about 20 or 30 Earth masses. So there is a limit for Pebble accretion. Only the Pebble accretion, we cannot explain the origin of heavy elements found in close-in gas giant planets, as I shown in the previous slide. So to bring massive heavy elements as 10 Earth masses or 100 Earth masses, we need to consider other processes. And that process is planetesimal accretion. I will explain later, but planetesimal accretion continues even after the formation of gap in protoplanetary disk. So planetesimal accretion is a key mechanism that can continuously supply the heavy element into the protoplanet. In this study, we investigate planetesimal accretion using numerical simulations and estimate how much heavy elements can be brought into gas giant planet during the formation stages. Okay, let me summarize the introduction shortly. The background of our study is chemical composition is useful information to constrain the evolution paths of gas giant planet. And the origin of massive heavy elements found in close-in gas giant planets are unknown, still unknown. And planetesimal accretion is might be a main source of massive heavy elements. So we will investigate the process of planetesimal accretion and try to answer the question, how many planetesimals can be captured by a gas giant planet? And is the planetesimal accretion the main source of heavy elements of close-in gas giant planets? And outlines of today's talk is I will talk about the planetesimal accretion in gas accretion phase, and which is investigated in Shibata and Ikoma in 2019. And then I will talk about another type of planetesimal accretion, a planetesimal accretion in planetary migration phase. And in the end, I will discuss about the evolution paths of close-in gas giant planets using the results of our studies. Unfortunately, I don't have enough time to talk these things in detail, so I only show the points of planetesimal accretion in gas accretion phase first, very shortly, and then I want to mainly talk about the planetesimal accretion in planetary migration phase today. Okay, so when does planetesimal accretion occurs efficiently? To answer the question, I introduce a feeding zone. This red area is a so-called feeding zone. The horizontal axis is a semi-regular axis, and the vertical axis is an eccentricity. And we consider that planet is located here. Feeding zone is defined as an area where Jacobi energy is positive. Jacobi energy is defined as the energy of an object seen from the coordinate rotating with the protoplanet. To explain it very simply, the radial distance from the protoplanet relates with the potential energy of that object, and the eccentricity relates with the kinetic energy of that object. If planetesimals have positive Jacobi energy, such as these red points, these planetesimals can enter the heliosphere of the protoplanet and can be captured by the protoplanet. On the other hand, if planetesimals have negative Jacobi energy, such as these blue points, they will never be captured by the protoplanet because they cannot enter the heliosphere of the protoplanet. Unlike pebbles, planetesimals do not drift in the radial direction so much, so planetesimals inside the feeding zone will be depleted by the protoplanet very rapidly. To accrete much heavy elements, we need to consider the process which can supply planetesimals into the feeding zone from the outside the feeding zone. One of the cases where planetesimals are supplied into the feeding zone is a gas accretion phase. Once the protoplanet mass exceeds a critical value, the protoplanet starts to accrete surrounding disk gas very rapidly. This phase is called runaway gas accretion phase. Feeding zone relates with the potential energy of the protoplanet. So if the protoplanet mass increases, the potential energy of the surrounding materials also increase. So the feeding zone expands and planetesimal are supplied into the feeding zone. Through this process, protoplanets can accrete planetesimal surrounding the planet. Planetesimal accretion in runaway gas accretion phase investigated by many authors. And this figure shows a simulation of our study. This orange plot shows a protoplanet, and it locates at 5 AU. These black dots are planetesimals, and initially they are located outside the feeding zone. So they are never captured by the protoplanet in this case. However, once the protoplanet starts runaway gas accretion, the feeding zone expands. And can you see this movie? Okay. As shown in this movie, as the protoplanet mass increases, the feeding zone is shown in the red area in this movie. Feeding zone expands and engulfs the surrounding planetesimals. So many planetesimals are supplied into the feeding zone, and some of those planetesimals are captured by the planet. From the numerical simulations, Chirashi and Ide 2008 found that planetesimal accretion rate depends on two timescales: planetary growth timescale and aerodynamic gas drag timescale. As I said, the Jacobi energy of planetesimals are increased by growth of the protoplanet. And at the same time, aerodynamic gas drag from the disk gas reduces the Jacobi energy because it's drag. In a protoplanetary disk, planetesimals orbits are damped by the aerodynamic gas drag, and the orbit is circularized. So eccentricity relates with the kinetic energy of planetesimals. So Jacobi energy is reduced by the aerodynamic gas drag. So in gas accretion phase, how many planetesimals enter the feeding zone is determined by the competitions between the mass growth speed and gas damping speed. This effect can be seen in this movie. I will show the two cases of simulations. In the left figure, growth time scale is much shorter than the damping time scale. And the right figure, growth time scale much slower than the growth time scale is much longer than the damping time scale. Okay, let's see the results. As shown in this movie, if the gas drag is stronger than the effect of mass growth, planetesimals are easily eliminated from the feeding zone. So in this case, planetesimal accretion is very rarely occurs in the right figure cases. To investigate how many planetesimals can be captured by the protoplanet in this gas accretion phase, we performed numerical simulations, various numerical simulations, and changes both timescales. Here we consider formation of Jupiter-like planet and construct various growth model, as shown in this figure, and change planetesimal radius, which relates with the damping timescale of the planetesimals. In minimum solar nebula, the amount of captured planetesimals is shown in this figure. This figure shows the results of each simulations and how many planetesimals are captured in each simulations. As shown in this figure, in minimum solar nebula, the amount of captured planetesimals is up to 2 Earth masses. Of course, we consider here is a minimum mass solar nebula. If the protoplanetary disk was heavier than the minimum mass solar nebula, the captured mass would be much more larger. However, it looks very difficult to accrete several tens Earth masses of heavy elements in this phase. And this is because the mass of planetesimals around the protoplanet is not so large. Planetesimal are easily depleted in this phase. So we need to consider the planetesimal accretion in other phases to explain the large amount of heavy elements found in close-in gas giant planets. Next, we consider the planetary migration phase. Considering the formation of close-in gas giant planets, we cannot neglect the planetary migration. When protoplanets migrate, planetesimals are supplied into the feeding zone because the feeding zone itself moves inward. So planetesimals located inner disk will be supplied into the feeding zone. Unlike in gas accretion phase, planetesimals would keep being supplied into the feeding zone in planetary migration phase. So we expect that much planetesimals can be accreted in this phase. Planetesimal accretion in planetary migration phase is already investigated by Tanaka and Ida 1999 using numerical simulations. In this phase, the source of Jacobi energy is planetary migration. So the accretion rate of planetesimals is determined by the competitions between migration timescale and gas dumping timescale. And Tanaka and Ida found the equation which shows how efficiently planetesimal accretion occurs in this phase. So it looks enough that we extend the result to our cases. But their study focused on the planetary migration of Earth-massive planets. On the other hand, we want to know the case of gas giant planets. So the mass of planets is very different in our study and in their study. The main difference between the cases of gas giant planets and Earth-mass planets is the effect of mean motion resonances. When mean motions or angular velocity of objects are related by a ratio of small integers, such as this equation, these planets are in mean motion resonance. This figure shows a geometrical picture of 2-to-1 mean motion resonance. In this resonance, every conjunction occurs at the same points, which results in the accumulation of gravitational perturbations. So mean motion resonances affect the orbital evolution of planetesimals, and their effects are stronger for heavier planets. In planetary migration phase, area of mean motion resonances also migrates, as shown in this figure. So almost all planetesimals are affected by the effect of mean motion resonances. In the previous study, Tanaka and Ida 1999, they artificially neglected the effects of mean motion resonances because they assumed that resonances of Earth-mass planets are too weak to affect the orbital evolution of planetesimals. But in cases of gas giant planets, mean motion resonances are strong, and we need to include the effect of mean motion resonances in numerical simulations. Okay, hereafter, we also focus on the role of mean motion resonances on planetesimal accretion. Okay, this is a method we used in our study, method and model we used in this our study. We consider the system of a central star, migrating planet, and planetesimals and disk gas disk. To reduce the calculation cost, we treat the planetesimals as test particles, and planetesimals orbits are damped by the aerodynamic gas track. During the simulation, protoplanet migrates from the outer disk to the inner disk in a regime of type 2 migration. We investigate the orbits of we integrate the orbits of planetesimals, and if they collide with the protoplanet, we judge that the planetesimal is captured by the protoplanet. By this simulation, we investigate how many planetesimals are captured by the protoplanet. And once the protoplanet reaches the inner edge of the disk, which is set as 0.5 AU in our model, we finish the simulation. Okay, let's see the results of the simulation. Here we consider that planetesimal are distributed from the 0.5 AU to 20 AU, and protoplanet migrates from outer disk to the inner disk. This red and green area shows 2-to-1 and 3-to-2 mean motion resonances. And in the right figure, right panel, I show the change in the cumulative captured mass of planetesimals. Okay, let's start the movie. As the planet migrates inward, planetesimals are trapped into the mean motion resonances and transported inward. This phenomenon is called resonance trapping. Resonance trapping controls the orbital evolution of planetesimals, and it controls the flux of planetesimals into the feeding zone. Due to the effect of resonance trapping, the cumulative captured mass of planetesimals shows a unique change with time. From the change of cumulative captured mass of planetesimals, we divide the planetesimal accretion into 3 phases. First one is a phase when the protoplanet migrates from 20 AU to 9 AU. In this phase, planetesimal accretion rarely occurs. And the second phase is when the protoplanet migrates from 9 AU to 3 AU. In this phase, the migrating planet accretes planetesimals very, very rapidly. And then in third phase, the planet migrates from 3 AU to 0.5 AU. In this phase, planetesimal accretion stops again. The sixth of the accretion phases is triggered by the aerodynamic gas drag, because the damping timescale becomes shorter in the inner disk, because there are much disk gases. Hereafter, let's see what happens during the planetary migration phase in detail. In the first phase, planetesimals are trapped into the mean motion resonances and transported into inner disk. So resonance trapping blocks the supply of planetesimals into the feeding zone. Due to this effect, the planetesimal accretion rarely occurs in this phase. However, as the planet migrates inner disk, the gas drag becomes stronger, and the resonance trapping is broken by the gas drag. It might be this phenomenon is called overstable libration, and which is found by Goldreich et al. 2014. Planetesimals trapped in the mean motion resonances starts escape from the resonance trapping due to the gas drag, and then supplied into the feeding zone. So once the resonance trapping is broken, planetesimal accretion starts. And the accretion speed is very rapid because planetesimals trapped in the mean motion resonances starts to flow into the feeding zone. So it becomes very rapid planetesimal accretion. However, at more inner disk, gas drag becomes so strong that planetesimals are eliminated from the feeding zone. So planetesimal accretion is stopped in this phase. Okay, this is the outline of planetesimal accretion in planetary migration phase. When the planet migrates in outer disk, where aerodynamic gas drag is weak, so Jacobi energy of planetesimals increases, but resonance trapping blocks planetesimals being captured by the planet. So planetesimal accretion does not occur in this phase. As the planet migrates inward, gas drag becomes stronger and starts to break resonance trapping. And Jacobi energy is still increased in this phase, so planetesimals are supplied into the feeding zone, and rapid planetesimal accretion occurs here. More inner disk, gas drag is so strong. Resonance trapping is broken, but Jacobi energy decreases, so the supply of planetesimals into the feeding zone is stopped, and planetesimal accretion also stops. From the numerical simulations, we find that there is a region where planetesimal accretion occurs very efficiently. Hereafter, we call this region sweet spot. So using the analytical formulas for mean motion resonances and gas drag and planetary migration, we derived conditions required for planetesimal accretion, which is shown by these equations. These equations are written in the fraction of timescales of between gas drag timescale and the migration timescale. So this timescale determines the location of sweet spot. The right figure shows numerical results of our simulation and the planetesimal accretion rate with the semi-major axis of the closed planet. As shown in this figure, there is a location where rapid planetesimal accretion occurs. This is a sweet spot we found in the numerical simulations. On this figure, we show the sweet spot obtained by these equations. The location of the sweet spot given by these equations covers the area where planetesimal accretion is very high. So we find that these analytical equations reproduces the numerical results very well. Okay, next, I will show the results of parameter studies. As shown in the previous slide, the location of the sweet spot is determined by the timescales of gas drag and planetary migration timescale. The figure shown the left figure shows the results of parameter study in planetesimal radius. The size of planetesimal radius relates with the damping timescale. So if the planetesimal radius becomes larger, the damping timescale becomes longer. And the sweet spot also shifts inward. And this figure shows the total captured mass of planetesimals in each simulations. As shown here, larger mass of planetesimals are captured for larger planetesimal cases. This is because large amount of planetesimals are transported into the feeding zone for larger planetesimal cases. Namely, the mass of planetesimals captured during the planetary migration phase relates with the mass of planetesimals transported into the sweet spot. Okay, next, I want to discuss about the relations between the mass of heavy elements and formation paths. As shown before, the location of the sweet spot is written with fraction of timescales, damping timescale and migration timescale. Fortunately, both timescale depends on the surface density of this gas. According to Kanagawa et al. 2018, which investigated type 2 migration using the numerical simulations, the migration timescale depends on the disk surface density. And the gas damping timescale also depends on the disk surface density of protoplanetary disk gas. So the fraction of timescale itself does not depend on the surface density of disk gas. This is a very interesting result because the location of the sweet spot does not depend on the surface density profile of protoplanetary disk. This right figure shows the confirmed exoplanets on the semi-major axis and planetary mass plane. The location of the sweet spot can be written as like this gray area. Considering the formation paths, we expect that close-in gas-giant planet had crossed the sweet spot during the formation stages. So we expect that many planetesimals are captured during the planetary migration phases for close-in gas-giant planets. Using the results of our simulation, we will estimate the mass of heavy elements brought by the planetesimal accretion for the cases of close-in gas-giant planets. We consider a planetesimal disk of minimum mass solar nebula. Given From the equation we derived, we know the location of the sweet spot. Given an initial semi-major axis of a planet's core, we can calculate the mass of planetesimals inside the initial feeding zone. And this protoplanet migrates inward and reaches the sweet spot. So we can calculate the mass of planetesimals which is transported into the sweet spot. These masses, these planetesimals have a potential to be captured by the protoplanet. According to our numerical simulations, the mass of planetesimals actually captured by the planet is only 10% to 30% of these planetesimals. So we set the fraction depending on our numerical simulations. Namely, we consider that the planetesimals initially located in the feeding zone, 30% of these planetesimals are captured by the protoplanet in gas accretion phase, and 50% of planetesimals initially located in this region are captured by the protoplanet in planetary migration phase. Using this model, we can estimate the mass of heavy elements in crossing Gaussian planets. The blue solid line shown in this figure shows the case of Jupiter mass planet in minimum mass solar nebula. And blue area covers the cases where we change the disk mass from 0.2 minimum mass solar nebula and 10 minimum mass solar nebula. As shown in this figure, as the initial core forms in outer disk, the mass of heavy elements also increases because the mass of planetesimals supplied into the feeding zone also increases with the initial semi-major axis of the planet. And Srongen et al. 2016 found that heavy element mass increases with the planet mass. So to explain this relationship with our model, we need to consider that heavier planets need to start their formation in outer disk. And this result is consistent with the current formation models of Gaussian planets. And some of those crossing Gaussian planets contains more than 100 Earth masses of heavy elements. From our estimation, we find that obtaining such large amount of heavy elements requires planetary migration longer than 10 AU, even in a massive protoplanetary disk. So our results suggest that such highly enriched planets might form by a gravitational instability model, because forming gas giant planets in outer disk is difficult for core instability model. This is a very interesting result found in our study, I think. Okay, in the end, I want to talk about the future work, what I want to do in Zurich and in Zurich. And in our model, we focused on the bulk heavy element mass or bulk metallicity of planets. So we did not care about the detailed composition like oxygen, amount of oxygen or amounts of carbon or CO ratio or other materials. However, future observations of exoplanet would reveal more detailed composition of exoplanets, such as JWST or Ariel will reveal the composition of hot Jupiter's atmosphere. And we expect that we can constrain the CO ratio or amount of C or O. As shown in this figure, H2O abundance is already constrained in some hot Jupiters. So to constrain the formation paths of gas-giant planets, these chemical composition are very useful because, as I said before, there are many ice lines in the protoplanetary disk. H2O ice line, CO ice line, CO2 ice line. So using the amount of C or O or CO ratio, we can constrain which area the planet comes from. To constrain the formation pathways of gas giant planets, we should consider the chemical evolution in planetary disk and include the detailed information of planetesimal composition in planetesimal accretion. This is what I want to do in Zurich. And of course, I want to try to other things like the internal structure model of gas giant planets, because JWST or area observes the atmosphere of planets, atmosphere of hot Jupiters. So we can not know the entire composition by these observations. To know the mixing or entire composition of planets, we need to know the interaction between the envelope and atmosphere of hot Jupiters. So it will be important physics, and I want to do work on those points too. Okay, let me summarize today's talk. I worked on the composition evolution of gas giant planets. The reason why I focused on this problem is planetary composition tells us the history of planet formation. And the origin of massive heavy elements in closing gas giant planet is still unknown. And heavy elements might be brought by planetesimal accretion. So we investigated the planetesimal accretion phases using the numerical simulations. We studied two cases, gas accretion phase and planetary migration phase. In gas accretion phase, about a few Earth mass, up to 2 Earth masses of heavy elements can be captured in minimum mass solar nebula, but it's not enough to explain the large amount of heavy elements in closing gas giant planets. So we consider the planetary migration phase. In this phase, protoplanets gathers much heavy elements from the wide region of the protoplanetary disk. And we find that there is a sweet spot where planetesimal accretion occurs very efficiently. And captured amount of planetesimals increases with the migration distance. Using the numerical simulations, we construct a very simple model to estimate the amount of heavy elements. And we find that for massive heavy elements, planets need to migrate more than 10 AU in massive protoplanetary disk. To accrete the more than 100 Earth masses of heavy elements, planets might need to be formed by gravitational instability. Okay, that's all. Thank you very much.
Thank you very much, Sho. Ravit, would you like to?
Yeah, sure. Thanks, Joe, for this very interesting talk. So maybe I ask if there are some questions first. Okay, I see
Sure.
Lucio already has one. Okay, Lucio.
Hi, very nice talk. I apologize that I arrived a bit later, so I might have missed a part where you would answer what I'm going to ask now. But anyway, I will ask it anyhow. My question is, the distribution of planetesimals that you assume in your model, is it following the disk surface density profile, or how are you actually setting it up? Because some of the conclusions that you have might depend on whether the planetesimals are distributed like the gas or not.
Okay, thank you very much. It's a very important point, and I assume that the distribution of planetesimal is same as a disk gas. Mm-hmm. And the amount is determined by the solar metallicity, right. About 1% of disk mass. And then I think this is a very big assumption in our model, of course. Recent studies show that the formation of planetesimals occurs efficiently around the snow lines. So this uniform distribution of planetesimals is not realistic. So we need to consider more realistic model as a next step. Thank you very much.
Yeah, I guess, if I can add very quickly, I think it would be interesting to see, how much inhomogeneity you have to put in the distribution of planetesimals to, spoil this nice result of the sweet spot. How much the sweet spot survives to changing the distribution of planetesimals in the disk. That would be interesting to see.
I think the distribution of planetesimals does not relate the location of sweet spot. Sweet spots only relates with migration time scale, migration speed, or of course the size of planetesimals affects the location of sweet spots.
Yes.
So if the yes, that is an important point. But even the size of planetesimals becomes 10 times larger, the location of the sweet spot moves only 1/3 powers of 10.
Okay.
Yeah.
So
but I think, sorry, just to say, but I think the point that of Lucius' questions is also what happens if you just change the distribution of planetesimals and it does not behave exactly like the gas. Actually, it can help you. You might be able, for example, if they are more concentrated actually in the region where you accrete more, it could be that you need less extreme conditions to
migration, for example. Yeah.
Right. So that's actually a nice thing to play with. I agree with that. Yeah.
Thanks.
Yeah.
Okay. So Andrea
yeah.
had a question. But okay, sure. Go ahead. Sorry.
Yeah. Okay. Please go ahead.
Okay. So Andrea couldn't raise her hand, but she had a question, and then Jason. So Andrea.
Yeah. Thanks. I don't know where my raise hand button went. I have a more basic question. Well, first of all, thanks for the nice talk. I was wondering if you can explain if this process is only relevant for Jupiter-type planets, or does it become less efficient for less massive planets? Can it also occur for smaller planets? The planetesimal accretion, I mean.
Yeah, okay, thank you very much. Yeah, it's a bit difficult point because if the planet mass becomes smaller, the effect of mean motion resonances also becomes smaller, weaker. And the sweet spot is formed by the effect of mean motion resonances. So the regime of the planetesimal accretion is different in the cases where mean motion resonances work effect or not. And the boundary is determining the boundary of the whether the mean motion resonance works effective or not is very difficult because mean motion resonances can be broken by the gas drag in our simulation, but it also can be broken by the collisions of planetesimals itself. So for Jupiter mass planets, it does not work, but for example, Earth mass planets, the mean motion resonance is easily broken by the collisions of planetesimals. So I think that Earth mass planets, mean motion resonance does not work effectively, but Neptune mass or other mass planets, it will work or not I cannot answer, sorry. I want to investigate that point.
Well, thank you.
Okay, Jason.
Hello, Sho. Can you hear me?
Yes.
Okay, hi. Thank you very much for your very interesting talk. I have a question about Jupiter and Saturn, mainly about the gas giants of our solar system. So, based on the current data of their metallicity, can we actually constrain their migration history or formation path? Yeah, but
with Jupiter and Saturn?
Yes.
Yes, but the amount of heavy elements in Jupiter and Saturn is not so large. It's about 20 or 30 masses for Jupiter and about 30 masses of Saturn. So it's enough to considering only the gas accretion phase only. If the protoplanetary disk was a few times heavier than the minimum mass solar nebula. So it is we cannot constrain. We don't need to consider the long distance migration for Jupiter and Saturn, and if we consider the asteroid belts, there are not so much heavy elements in our solar system, and as shown in our study, many planetesimals are transported into the inner disk by the planetary migration phase. So if the Jupiter migrates very long distance, like 10 AU or 20 AU, many planetesimals are supplied into the asteroid belt area. But as shown in our solar system, there are not so many Planetesimal or asteroids there. So I think that Jupiter does not migrate for long distances, I guess. But we need to consider many other things for the cases of solar system. So we need to care. We need to consider more further.
Okay. Yeah. Thank you very much. So based on, I think what you are saying is based on the current data, it is possible for Jupiter and Saturn to form close to their current location, right?
Mm-hmm.
Okay.
Yeah.
That's good. Thank you. Thank you very much.
Okay, thanks. Any other questions?
So, hi, Sho. How sensitive are the results on the planetesimal size? So, in particular, what would happen if we decrease the planetesimal size to, let's say, millimeter size? That will be the case for Pebbles. What would happen?
If the Planetesimal was very small as Pebbles, no solid materials are supplied into the physics zone because around the Jupiter mass planets, there is a deep gap, and pebbles are eliminated by the effect of disk gap. So if pebble accretion does not occur in this phase, but the size of the planetesimals are 1 kilometer or 100 meter or meter sizes, the sweet spot moves more outer regions. In that case, the amount of heavy elements captured by the protoplanet will reduce, I think. Is it okay?
Yes, of course. You are right, of course.
Okay, thanks, Claudio. Any other questions? Okay, if you come up with a question, Sho is at the Institute, so please feel free to ask him or write him an email. So let's thank Sho again. Thanks a lot. And
thank you very much.
Yes, I wish you all a very happy weekend and see you next week.